The title of my talk is What the Heavens Are Telling Us. It's pretty certain that since the beginning of human history, people have been looking to the skies. And as I go through this, they're always trying to wonder what their place is, our place is in the universe, and then wondering what the future will be. And so I start off, I just want to show you where this is going to go in the end is when we're going to talk about a certain type of supernova. And this photograph right here, oops, sorry, let's back up. Oh, I'm kidding. This is actually a supernova right here in this galaxy. They are incredibly bright objects. And I'm hoping before I die, we have one. We could have one. I'll talk about that in a moment. We should have one per galaxy per century. But the last one recorded was in 1572. Was Tycho Brahe recorded. He gave it the term nova, which means new thing. They didn't know what it was. There's another one they believe was recorded in 1054, Chinese sources, which was recorded as a supernova. And we'll get to this. One of the remnants of a supernova is a nebula, and the Crab Nebula is remnants of that. Now I want to start off just why is this interesting. In many ways, people don't realize how much astronomy has had on the influence of people's lives. Many believe that astronomy was the beginning of science. People looking to the skies saw that things were repeated, the seasons, the length of the days. Certain planets come at this time of year, they disappear this time, certain constellations. And one of the interesting things I always tell my students is people forget that the 7 days of the week actually are based on the 7 brightest objects in the sky. Now English has kept Sunday and Moon Day and Saturn Day. Today is Thor's Day. Okay, we took in some Norse. But if you speak other languages, particularly if you speak Spanish, you can go through the days of the week where Martes is Mars, Miércoles is Mercury, Jueves is Jove or Jupiter, Viernes is Venus. Then they took the Sabbath for Sábado. They got rid of the Saturn, which we kept. And they got rid of Sunday. They used Domingo as the day of God, the day of the Lord. So it's kind of interesting. Now the whole idea of the month actually is very religious because people counted the years that way. And we, as Christians, most people are Christians, Easter is the only holiday we have that seems to follow that. A lot of other have gotten. And I'll mention the signs of the zodiac, very popular still. And I'm not going to go there in regards to whether it's validity or whatever, but we'll talk about that in a bit. I also wanted to mention that in the scriptures, the Star of David, the Magi seeking the star, the fact that anybody who wants to talk to God has to climb to the highest elevations. Moses has to go up the mountain to get the commandments, the transfiguration, Jesus is up on the mountain. The idea was you had to get high up to get closer to the heavens. The idea was the heavens were perfect. That's where God was to be found. And the lower levels is where hell is and where God is not to be found. I had to put one stained glass. This was one of my favorite things because this was a stained glass window from a church where I worked in Chicago. These are the two groups of people that encounter, that see the star. We have the shepherds here and we have the 3 magi. And I bring them up because it's interesting. I think they are the beginnings of science. In many ways, people laugh about astrology now, but the fact was science in its early days, particularly astronomy, was done by people who wanted to predict the future. They were looking at the skies. That's what these 3 were trying to figure out what this star is. The other reason I wanted to bring this up is people have tried to analyze the whole story. What was that star? I like to go, when I work at these different parishes, I go in there and I look at their nativity scene. And sometimes you see a little star, it looks like a little meteor going over. The argument is it most likely would be a supernova. It happens suddenly, and we'll see later that these things turn on in the course of days. It would last up to 2 months, and then it would go away. The problem is nobody has any record of a supernova at that time. And it's an interesting, the Adler Planetarium in Chicago actually wrote 60 years ago, tried to analyze this. It would have been a supernova if you followed the story, but no evidence yet of it at that time. I put this up as a counterbalance before, as these are stained glass windows of the cathedral in Cairns, North Australia. I was there some years ago, and it was interesting for me because actually the whole idea that stained glass windows, they're showing creation is a part of God's domain, which it is, and I just find it kind of interesting. I think that's kind of supposed to be some of a supernova thing there, but you see this galaxy and you see some planets and things, kind of an interesting little twist to the story. Okay, so what I want to say is the following. I put this up for I know there's chemists out there, but the basic question is, so I'm a particle physicist, and I went into astrophysics. We're still asking ourselves, what is matter? What is the universe made out of? Okay. Now, if you're a chemist, and a lot of you have studied chemistry here, and you say basically everything can be made from these building blocks. They always make it like little building blocks. Every element is up there, and everything on this planet is there. And you basically can take it one more step, as you know, and you learn it, is that protons and neutrons and electrons are underneath all of this, but you just stack them up, particularly the protons and neutrons in the nucleus, and you create this list. Well, it turned out as time went on, people started finding matter that was not on this list. And it's a little plug for Fordham, but I wanted to list this. He was a faculty member. This is Victor Hesse, who was a faculty member at Fordham from 1938 to 1958. He came there shortly after receiving the Nobel Prize in Physics for his discovery of cosmic rays. And this is in Germany. These are little kids. They would get in these balloons and go up and take data. It turns out that as we're sitting in this room, strange and exotic particles are flying through this room as we speak. There are neutrinos that are actually coming through the floor, through the surface, through the earth. And nobody knew this because we didn't have the equipment to measure them. They actually went out and they found these things, and I use the term here, strange. They didn't fit the table. They were not a proton, they were not an electron, they were not a neutron, and they weren't a gold atom, and they weren't a silver atom. They were none of those things. And what they were finding was these strange particles somehow were coming from space, and the question was, what are they, and how are they getting here? Now, I'll start to talk about some of my stuff. The problem with this field of cosmic ray physics is these exotic particles exist, but the time, and so they're per area, per time, per weight, is very small, okay? If you find one, you're lucky, but you may wait there for another year before it happens again. So physicists got wise and said to themselves, what we have to do is create the circumstances. We're going to create an accelerator to find these particles. And I ended up working at Fermilab, which is about 40 miles west of Chicago. And this building right here is that building right there. And you see this huge ring here, and my experiment was right in these halls right here. In this region, this accelerator, they try to create the circumstances that exist in space that create these particles. And so when it was running, and I have it written up there, it stopped about 2010, but up until 2008, before CERN's new update, which is the Center for Nuclear Research in Europe, it was the highest energy accelerator facility in the world. And they would collide protons and antiprotons, set up an experiment, and wait for a whole series of these things to be created. And they have to go through the data and have them and put them together. I just want to mention this. Their energy levels it's 2 tera electron volts. If you think of a 1 volt battery, this is 2 times 10 to the 12 of those. CERN, which is the current highest facility, is about 7 times more energetic. To get a more energetic place, you have to keep building a bigger and a bigger ring. This is the last accelerator CERN that will ever be built by humans. It's just too big. They have to have a new technology. I bring up this because there I studied basically a series of particles which are not on the list. And I'm just going to show you, this is their logo, by the way. Interesting thing about Fermilab, in parts of Illinois, they're trying to bring back the buffalo herd. So you see there's lots of land out here. They actually would let the buffalo kind of live there naturally and eat the grass. And then it's funny, they put these geese in there, yes, Canadian geese, but one of the things they found was, in order for you to collide and direct these electron beams, or their protons and antiprotons, you have to have all these magnets. And all these magnets mean that things get hot, and the water, this little pool of water here would never freeze. even when it was minus 16 degrees Fahrenheit on a beautiful January day, this would be steaming. And these geese figured it out. They wouldn't leave. This was a big problem. So they had, geese were clogging hundreds of them. And it was kind of neat to watch, but anyway. All right, so if the particle physicist said no to the chemist, this is our periodic table, this is what they would do. And what they say is that all of matter is composed right here, more or less. There's a couple missing things. But that the world, as we know it in regards to mass, matter, is made of quarks and leptons. And I'm not going to go on the pieces of this, but you can actually put these quarks together and create a proton. And there's the electron down here. And these neutrinos were very difficult to find. They're light, they're very fast, they're neutral. But they did. There was always a missing link. But this is the piece. And the pieces over here, the photon, the gluon, these two particles were those representations of those four forces you know about. Gravity's not on the list, but gravity being one, but here's the electromagnetic, here's the strong force, and then here's the weak. They said this is everything. And so I did this for my doctoral thesis. I measured a lifetime of one of these mixed with another quark. And I wanted to show kind of the progression is, so I was on the experiment, we'll go back, in which we actually found the top quark, which was the last missing piece. Now the problem is, as you go down this list and you go this way, they get heavier and heavier and heavier. And there's a rule in physics, when something's heavy, it will decay to something less heavy. So you get these things, they just last a picosecond of that, and they're gone into something else. So we actually determined, so this is, I'll show you if you want to squint. That's me right there. This goes to show you how big these experiments got. Now this is 1995. I think then it was on the order of 160. This experiment blew up to 300. And by the way, your second page of your thing has to be all the institutions that are involved in it. So this was a big controversy because some of these journals, you only get 4 pages. And they asked them, could we actually have our publication list as a publication that we reference? And then have it give us the 4 pages. They said, no, you have to print everybody's name. But anyways, back in this was, we actually, the experiment, me and my closest science friends back here, sorry, measured this top quark, and it was the last one. It's about the mass, it's 176, they say, it's about 174 GeV per c squared, which is about the mass of a gold nucleus. So, a very heavy thing. Now, one of the things I wanted to talk about was the experiments got so big that many of us particle physics people didn't like it. It was too much. It's like living in a big city. You're part of this huge thing, and people were looking for smaller science. So when I got to Chicago, I said to myself, I was going out to Fermilab trying to get connected there. And I met some former friends. Keep your friends, because your friends become big shots sometimes in other places. And some of them were running science programs. Argonne National Lab is another lab in the southwest part of the suburbs of Chicago, which is a more multi-purpose place. They do physics, but they also do alternate fuels, chemistry. They have a photon source there. They were doing this little experiment. This is it right here. It was out in the middle of a field. And what they were doing was looking for cosmic rays. They were looking for high energy particles, just like Victor Hess was. And their idea was a really fairly simple one, is that the atmosphere can act as an agent for a charged particle to come in and actually create a certain type of light. And that light would be focused onto these. You can see these are very shiny little mirrors here, which would focus it up to a camera, and it would take a picture of the energy. And that would actually allow you to see if you had these happening in your, this was going to be taken as a prototype out to Arizona, by the way. Outdoor physics in Illinois and Mobile and a lot of places for various reasons, mainly rain and clouds, doesn't happen. But they were testing it there out. This was, you can see there was a little tent. We'd have to pull it out of the tent. Keeping on this same theme, so by the way, physicists love acronyms. So this thing was called the Trice Detector for Tracking Imaging Cherenkov Experiment. So Trice right here, they throw a little R in there. So this same group I was working with at Argonne, I said, you know, we should do some physics where let's try to get back to like small rooftop stuff. Is this possible? And one of the researchers there, Steve Coleman, he had done some research in finding that maybe there's a way to actually find cosmic rays in a local space. And if it was easy and cheap to make, his plan was we could put these at every school, every college, every university, and track the whole United States. So now you have the huge area that you could cover, and then you could sit there and wait. All these people are waiting for cosmic rays. And it was a very interesting idea at the time, and I'll show you how it worked was. So this is the physics building at Loyola Chicago. You can see it was a beautiful day in winter, snow on the ground, and up here we attached an antenna. And what you would do is the following. This is a little schematic one of my students drew. Everybody loves a schematic. This is a TV station here. It was Channel 4 in Davenport, Iowa. And if you go 130 miles from where you are, you will reach the curvature of the Earth, where whatever is over 130 miles from you, if it's sending out a signal, it can't come straight through to you. It has to go up and then down, so up through the sky. And the idea was it was going to try to detect anything up there. It's much like radar, is really what it is. But the idea was to use this as a cheap way of seeing if we could come up with a way to determine that there was a charged particle. Now, the way this worked then was analog. By the way, my student came up with his own schematic here and his own acronym here for Loyola University Cosmic Event Detection System. What happened was, as you know, shortly thereafter, this TV went to digital. So that was another story, but I'll just show you what we saw. This is a schematic of just to show you what, I know it's uploading something from Wikipedia. Anyway, so what happens is a very energetic particle, typically a proton, when it comes into the atmosphere, much like a meteor, it creates what they call a particle shower. When it hits, it's almost like a shield or a target. All that energy turns into other particles. And it forms almost this lightning bolt of energy. It's very quick and very narrow, much more narrow than a lightning bolt, but very similar. And our plan was to somehow detect these things. Now, as you know, if you've been to Chicago, it is a big airport. This is KORD, which is O'Hare here. So one of the things we knew we were going to find was if you were actually looking for these cosmic rays, you're going to see lots of other stuff. And what you see are airplanes. And this is, we would take a thing, you can go on a website and look and see who's currently landing, taking off, flying over. And we kept seeing all these squiggles on here, and we knew these are planes. And actually, if you know your Doppler shift stuff, the frequency is higher on approach and goes lower when it goes away. This is the kind of the timeline right here. This would be a plane which is approaching the site, the antenna, and then going away. And that's basically these planes and they were landing right over us. We're right at the 42nd parallel. One other thing we found too were meteors. Most meteors never hit the ground. There's pebbles flying into the atmosphere as we speak, and most of them just burn up there. And we were actually seeing them. These little blobs were meteors, and you can see some planes here too. The problem we had was two things. One was digital TV appeared, and so therefore this whole system didn't work. The second was we did an analysis of how this data was being taken. The speed of that cosmic ray was too fast for the speed of the electronics to catch it, although we were seeing these little things. This idea hasn't died. There's people in Utah who are actually setting up, what they do is they set up a transmitter behind a mountain and then put their equipment on the other side and are trying to do the same thing. It's not dead, but the idea of having it mass produced is not going to happen. So from that, I want to move onward. So the next thing was, so like I said, a lot of us ended up trying to do some astrophysics stuff, smaller. And the fact is one of the things, this is an old plot of this. So Edwin Hubble in 1929 was studying Cepheid stars. And Cepheid stars are a type of star, we'll see, it was what they refer to as a standard candle. Everybody knew how bright they were. If you know how bright something is and you don't see it very bright where you are, you can come up with a good calculation about how far away it is, okay? And one of the amazing things as he was studying these stars, he's tracking how far away they are. And I'll show you here in a second. He could figure out how fast they're moving by how their spectra was shifted. He decides to plot where the object is located, its distance, as well as its speed. And when he plots that, this is his data here. It's kind of rough, but he basically fits it, kind of almost eyeballs it with a ruler, and sees that it actually is linear, which was amazing for him, because what this proved was that the stuff that was farthest out was moving faster than the stuff that was closer. So it was this idea that the universe was expanding. Now, people who were beginning to really understand what the Big Bang Theory was basically saying, well, this makes sense. If there was an explosion, if you got an explosion here, you see all that stuff get expanded out away from that. And this idea was, okay, interesting. That makes sense, but they were trying to understand what was going on. Now, a big debate comes up because one of the things I didn't mention was that perfect place out there, space, the heavens, because it was perfect, it had all these funny things that people gave to it. The motion of everything out there was supposed to be circular because circles were perfect. That was debunked by about the 16th century. The second one wasn't static, that it had its period, but it never really radically changed. Okay, it was the same year after year. You could predict it, but things didn't change. And this idea that the universe was expanding outward and getting faster at the edges was very strange. And so a debate starts. So let me show you this before I go there. How do you figure out how fast something is moving? So this is a light spectrum of redshift is basically this little number here, Z. It basically tells you how fast something's moving. This one's moving much faster, this galaxy. But what you can see is the output of light. These are your emission lines. And if you take a look here at this 6,600 or so, or this is angstroms light, it gets redshifted, pushed out to about 7,300. And the idea is when you're looking at something and it's going away from you, and particularly if it's a light source, those wavelengths get stretched out. This is what they refer to as redshifting. The light looks redder to you than it should be. It didn't turn red. And actually the opposite is the case. If it's coming towards you, it looks bluer than it really is. Okay, so this is how he figured out. By the way, I should mention, I have a little source in here. If you want to read, Robert Kirshner is one of, and I'll talk about, they got the Nobel Prize in Physics in 2011, this group, to further prove what Hubble had done with these Cepheid stars, and we'll get to that in a minute. So you'll see this down here, this source. It's a really good book that you don't have to be super techie to understand what's going on in there, and it's a good source to read. All right, I put this poster up. I went to this play. So this play gets circulated called Creation Story, and it's a funny little play. It's basically a trialogue between these three. So we know who this is Albert Einstein. Here's Edwin Hubble. Now he's basically the experimentalist. He comes up with the data and says, look, I have this data that shows you the universe is expanding. These two guys, by the way, George Lemaitre was a Catholic priest. He's not a Jesuit. He went to a Jesuit high school, and they refer to him as the father of the Big Bang. He actually did the math that proved why you would expect the universe to expand. Interestingly enough, Einstein wanted to hold back on this idea that it was expanding in his theory. He had to throw in this constant to get it to match the data, which they call the cosmological constant. And these two have this kind of dialogue about what goes on and how it makes sense. It's a very interesting play. But the bottom line is this was a huge, huge issue. And in the end, he was right. Okay, we'll get to more of that. So, as we move on, the question is, if you could find some standard candle, some object in which you know precisely its brightness, just like he did. And there were problems with Cepheid stars. They had their issues in the long run. You saw his data set had a lot of variation. If you could find an easy one that's knowable, and the second one is that characteristics are easy to measure, very important for you, and then you need a lot of them. That's always when you do your experiments, you need a lot of statistics. You need to get as many as you can to prove that what you have is for real. The answer, which I'm going to come to, and this is the final part, is that what you want to study if you want to see the expansion of the universe are type 1a supernova. Okay, it's a type of supernova, and we'll talk about that now. All right, I took this from my astronomy class, from the textbook down here. And so here's the story. Here's our sun. Our sun is a middle-aged star. Lower mass, not super high, but not super low. It has a lifespan. Now, if you want to go through the theory about what's going to kill us first, okay, anybody have any idea what's the most likely problem we'll have as humans on this planet surviving in the future? Huh? I'm sorry? Climate's one of them, brought on by, it can really be radically changed by this one thing, which has happened before. An asteroid, okay. This is our biggest fear. That's our first fear. Because it's happened before and it'll happen again. Now, we maybe have the technology that we can turn it somewhere or blow it up before it gets here. But 165 million years ago, one hit us, and strangely, the story is we're here now because of it. We can talk about that later. But so here's the theory: is the next serious problem we're going to have is the sun burns out. The sun will burn out. The sun is currently 5 billion years old. It's a middle-aged star. And when it burns out, so if you go through the astronomy stuff, it has to get enough mass that the core gets hot enough that fusion can occur. And then this balance occurs where gravity wants to pull all that mass in, but as it's burning, the energy is kind of pushing it out. So it's almost like this just kind of happy median. What happens is it burns over time as that mass gets consumed and the gravity loses out. And that sun will explode into a red giant. The outer layers of it are going to explode because there's not enough mass to keep it pulled in. When that happens, it's going to be knocking at our front door. I think one of the theories is be very close to Earth, okay? And we're not going to like that because it's going to be right out there. And anyway, as it goes through, what's interesting, the core, if you study this, so the hydrogen is fusing to helium. The core becomes helium, and then that core becomes carbon. It keeps compressing. Now, if you do your math and know your chemistry, helium is a 4. If you do 3 of those, you'll get a carbon if you kind of jam them together. This little core here becomes eventually a white dwarf star. That's the future end of the life of the sun. And what happens is when that outer part finally explodes completely, that's the nebula part right here. And that little carbon core will just slowly cool down. You can see this is temperature here. It will keep cooling down until the white dwarf will turn into a black dwarf. Okay. We'll talk about these in a second. These are the source of the type 1a supernova. Our sun will turn into a white dwarf. Some of the heavier planets up here, I should mention, we'll see this in a second, they go through a similar process, but their core is a little bit different, and you'll see why in a second. Now, this little white dwarf, in order for a supernova to occur, it has to have a nearby companion star. About 50% of the stars out there are binary. And what will happen if there's a big companion star with lots of mass, gravity kicks in and it starts pulling in some of the mass into its very hot, it's almost like a little, waiting to explode, okay? That mass will be pulled into the part that this will explode. And that's when you have basically fusion takes over again and you have this supernova. Okay, so for the supernova to occur, you have to have this white dwarf star, which has a nearby companion that can pull mass in, and the thing explodes into this huge bright object. Now, one of the things, so I'm going to tell you about the research I've done and where it gets tricky in all of this is that, and maybe we'll go back one more. When we look at the most important thing in determining the future and the characteristics of a star is its mass. And these heavier ones have a slightly different path than this one here. And I want to bring that up because the problem you have, and this is always kind of true in science, but okay, so this is basically a little flow chart. These are all supernovas right here. And what you do is look at their light output and you do a spectral thing here and you look at the different lines and identify them. And one of the big things is if you make a distinction whether there's no hydrogen or there is hydrogen, you end up with the type 2 down here. And if you come along and there's no hydrogen but one has silicon and the other one doesn't, you have either the type 1a or the type 1 also. This group right here they refer to as core collapse. They're the heavier stars that will collapse into a different core. Now the reason I want to bring this up is this is typical. If you're looking for supernova in the sky, and I'll show you how they do that, you are going to get all 4 types. You're not going to know. Now, you could say, well, you could go off and do this spectral analysis and go look to see if there's any silicon or no hydrogen, and then you're sure. But they don't do that. It's too much work, okay? So what did they do? And this is where the genius part comes in. This is where you get a Nobel Prize if you come up with it. So here's what I want to show you. This is the absolute, this is how bright it is. This is the type 2, the type 1, here's the type 2. A couple things I want to show you. Notice with the supernova, it turns on very quickly, in the order of days. There technically could be a supernova tomorrow, and we would see this incredibly bright object in the sky, which would get very bright in the course of about 4 or 5 days. And then it would be very bright for a while. You can see it on the order of about 10 days here. And then it would start to putter out. And eventually, within less than a year, it would be completely gone. Okay. Now what these guys did is the following: is instead of looking at what light is coming out, if you look at how much light is being emitted by the supernova per day, if you can, you could fit this, they refer to these as light curves, to tell you if you had a type 1 or a type 2. Now the big giveaway with the type 1 is they're much brighter. This is minus 19, these are like minus 17. The other thing is they turn off quicker. This has this kind of elbow part, and then they both kind of die off. Now we'll see the problem is when you are looking for any supernova, you want to get as many as you can, but then you want to have enough of an analysis program that you chop out all the bad ones, but keep as many of the good ones as you can. Now I just want to show you, this is the redo Hubble diagram. If you take some of the, this is from the type 1a supernova, you'll see the plot is much more uniform. But you'll notice when you go farther out in space, the errors are worse. So this is kind of a problem. You want better, smaller errors, okay? So what do you do? How do you do this? Well, you have to find yourself a mountainous place, a dry place, a dark place, an accessible place, and this little place right here is Cerro Tololo, Chile. Up on the top of that mountain are these series of telescopes. And this is run by a consortium. You have to get, your time in. And basically what they're going to do is they were given, this is all like, you have to go and put your proposal in, get your days in. They were given 525 nights, clouds or not, over 5 years. So they typically do it starting about now. And they do it through remember this is the southern hemisphere, so they're starting their summer. And what you do is the following. So up here, inside these telescopes, you have a camera. And what you do is they're showing you, this is the southern hemisphere, is the South Pole up here. This area, the telescope is basically computerizing, taking pictures of the sky in little bites across here and through this whole region every night it can, okay? And what it does is the following is, it takes those pictures, I'll come back to that in a second, and it digitally subtracts the sky light from one night from the other. So what they do is, here's a picture of one day, and then here's a picture. This is not necessarily the next day, this is the next time period, which could be 2 or 3 days. Now, that makes life difficult for you, you'll see in a moment, particularly when you're near the peak and you don't get enough points. What they'll do is subtract these two, and then they see one thing is brighter the next period. That means that thing is a supernova. It's turning on, okay? Now, I'm going to go back here. One of the things they'll do too, just to kind of the analysis part, is on the lens of those cameras, not only are they taking data, they will actually put different filters on, and these are different filters, and these are wavelengths of light, some of the visible and some not. And they put those on there to see what light comes through. And that's kind of a verification to give you multiple plots of what you're going to look at. I'll show you here in a second. These are kind of interesting plots too. This is the typical experimental problem. This is efficiencies. And you'll notice that some up here, it kind of falls off and it isn't so well. There's little gaps in this. These are the little things that drive you crazy as an experimentalist. All right. This is real data that we were looking at, and I'll show you why in a second. This is from this paper. This is what real data looks like, and this is how it would work. You see a series of plots and you fit them, and it's basically a computer program here. And they're showing you, they took a plot of all of their type 1a supernova they got in this data set and plotted them here. And you can see the turn on and the fall off, very sharp peak. The giveaway right here, you see the minus 19. And anyway, so that's just I want to show you what real data looks like. Now here's why you have to separate these. This is some data that we simulated. And what happens, this is a version of the Hubble plot. Redshift is your velocity. This is the distance modulus right here. It's basically a distance parameter. And these little red ones here are type 1a supernova that are following Hubble stuff. If some of these get in, your physics gets messed up. okay, you are in trouble. You can see these are off the plot. They're not following. If you go to fit this, you're in trouble, okay? So you want to get rid of these. So one of the problems is in most physics stuff, everybody wants the good stuff and they don't want the bad stuff, but everybody ignores the bad stuff, but you need to understand it. So what my student did, well, we worked on this for a couple of years, was this. So you run simulations. We don't have the data now, but you try to simulate the data as real and as exactly the data should be, but then you play with it. And what we did was the following: is we took all the junk type, the core collapse, the bad one, supernova, and threw them into the program that tries to find the good ones only. And what we found was, and people were worried about this, was it said some of the bad ones were good, more than a few. And you start to get nervous as why is that? Now, one of the reasons was in your simulation program, when you had the supernovas that are the bad ones, you didn't know how good you didn't know them that well. And one of the things we did was we make some of them brighter and make some of them less bright. You'll notice that we made some of them brighter. More of them got picked up as being the good things when they weren't. And we made them less bright, less of them got picked up. So what was the problem in all this? And I'll just show you. Here's the thing. So here's how it works, is basically these are what they refer to as templates from a certain experiment. Here's the Sloan Digital Sky Survey. This is a certain type you'll see right here of supernova. And this is the year that they found it. I'll tell you its magnitude. This is in a certain band, those color bands. And what we found was these were all the bad ones that were simulating bad data. And then if you look over here, these were the number of them that actually were labeled as a good event. And this is one of them here, and you'll see what happens. This was actually a 1B, which is a bad one. And these are the different filters, by the way. So here's the G, R, I, Z. And you can see what happens is the one that it fit really bad data points, these huge errors here. And so we looked at this, and it looks like it thinks this is a good type 1A, but it's not. And you'll notice this is relative. You can't get a sense of the absolute brightness. The problem is, how do you separate these from the mess? And so we'll keep going. I'll show you what I had to put, and this is my student, that's Jefferson. I put him up there at honorable mention. So we're still putting this together. This is just to show you our little collaboration point. Basically what he did was the following: was if you mess up these bad ones, a lot more of them start to look good. So what do you do about this? Okay, these uncertainties basically are going to mess up your physics. And here's why it's so important. If you don't have a nice pure sample, you start to get stuff that will contaminate and mess up your physics. But the problem is, when you make really stringent cuts to get rid of the bad stuff, you do throw out some of the good. And here's what the important thing, and this is the most important plot that you'll probably see on here. So here's the idea. When I was teaching astronomy here at Spring Hill College in 2002, we used an excellent book. It was recommended to us by the Vatican Observatory. Everybody was using it, University of Arizona. And in that book it said that the future of the universe is this. Yes, the Big Bang occurred, and all this stuff is expanding. And it's cooling. And as it cools, you get more mass. And you get more and more mass over time. Now, when you get more and more mass, gravity kicks in. Gravity wants to bring it all together. It's an attractive force. The argument was, and you can see this kind of in this recollapsing, is that eventually all the energy cools to matter, and it comes and collides on itself. So there was the Big Bang, they called it, would turn into the Big Crunch. And they thought that this was a cycle that's been going on forever. It turns out that's not the case. Now there's a couple. Coasting right here is basically Hubble, means it just keeps going at the same rate, same acceleration rate. What they're finding now is not only is the universe expanding, but it's accelerating. And the acceleration is accelerating. Now, when you study physics, they'll tell you there's the change in position with time is velocity. The change in velocity with time is the acceleration. Anybody know what the change in the acceleration with time is? Jerk. The jerk is actually increasing. Now, You'll notice what made this all difficult was all these plots come together at one common place. And where they separate in the theory is that you need to get deeper into space. And that's the wonderful, fascinating thing about the Big Bang is when that stuff was formed and got sent out there, if you go deep in space, you're seeing the universe as it was in the past. So if you get out as far as you can, now we're about 14 billion years-ish. If you can get back into, you will see the beginning parts of this. Now you'll notice as the deeper they get into space, the errors get bigger and bigger. But they're getting better at this, the point where you can see these new numbers, the newer stuff. And this is the whole idea of these experiments. If they get more and more of these supernova, this plot is going to become more distinct. And what you're seeing is the accelerating is starting to take off. Okay. And so, what does that mean for us? What does that mean? Yeah, it's actually, everything will just disappear and freeze. The big chill, they're calling it, okay? It's just everything. Now, I've not heard a time frame on this. I don't think we have to worry about it. But it's an interesting phenomenon that basically the Big Bang was one event and it will just all putter out. Kind of sad. All right. Now, here's the interesting piece. This is where the physicists are most intrigued. And this is probably the biggest question of the whole thing. I started off by saying, now, I said two things. We look to the skies and we're worried about the future. Well, we are worried about the future now because it will chill down. The second is, how do we understand what's going on out there in light of the physics we know now? And the answer is we don't. The idea is that this plot they showed back here, the model that predicts this part right here, this acceleration, they kind of have to do a little balance sheet and to figure out how this is all going to work. This is a pie graph of what they believe all of the matter of the universe has to be in order for this accelerating universe to exist. 75 plus 21 is 96% of it is completely not understood. This dark energy, and they give the term dark energy, dark matter, is that we can't see it, we can't detect it, we don't know what it is, nobody knows what it is. Okay. This dark energy has what they call a pressure that wants to push out. So gravity wants to push in. This is why the universe is expanding. There's so much of that out there somewhere, they don't know what it is. This 4% is basically everything from that chemistry table to the particle physics table, us, the universe, stars, planets. This is it. This is what they refer to as normal matter or baryonic matter. The dark matter they have here is another wedge, which is a fascinating little piece of physics too. In studying galaxies, they can watch the stars move. One basic principle of physics, and you can do the calculation, is that gravity is 1 over r squared. If you set that equal to centripetal acceleration and solve for the velocity, you find that the farther you get away from your anchor, so the farther, for instance, the planets are from the sun, the slower they move. So the farther you get away, so Mercury's moving much faster than we are, we're moving much faster than Saturn is. Okay. When they've studied the stars in the halo region, which is around the central part of a galaxy, those objects, some of them are speeding up instead of slowing down. And that has them boggled down too, because that says there's some kind of gravitational-like substance there speeding them up. That's why they call it dark matter. And we can come back for the questions on that. All right, so here's the kind of funny part. This is little conclusions and ask a few questions. So we really only understand about 4% of the matter in the universe. And by the way, 98% of that 4% of matter is simple hydrogen and helium. There's a good news, bad news. The question is, what is dark energy and dark matter, the other 96%? Now there's a group, one argument is we don't have to go find this, we just don't understand how gravity works. So there's a group at Argonne whose job, they're theorists, they're trying to come up with models of a gravity that would work in our environment that would be different, much different in a different environment in space. Nothing there yet, but they're working hard. One of the things that's fascinating too about these supernova, which I kind of skimmed over, was this 98% of the universe is hydrogen and helium. Everything else on that periodic table, including carbon, oxygen, you organic chemists out there, was from basically the fusion within stars. And so what you can really argue is that the heavier elements came together through fusion, particularly through the explosion of a star, and that we and our universe are basically the remnants of exploded stars. We are, in a sense, stardust. So we are composed of stardust living in a universe that is accelerating. Can't explain how it's happening, but it's going to come to the big chill, okay? And I'm going to conclude with that. I thank you for your time.